Okay, great. Um, okay, this week we're going to do something a little different. I don't think you've been exposed to this instrument in lecture, so I'm pretty sure you haven't because it's really not an instrument that surveyors use. It's mostly used by construction people, but it is a different way of leveling. So today we're going to go out with what is called a laser level, and I'll explain in a minute how that works. What we're going to do today is we're going to take a series of elevations along the Guy West Bridge, and the end product today will be a drawing that you prepare to scale on a separate 8.5 by 11 piece of graph paper showing the profile of the bridge based on the elevations that you're going to measure. Okay, so let's go over CE9L Lab Exercise 6.pdf, which is up on the screen right now. So we're going to backsite TBMW, the same manhole that you backsited last week. Let me stop for 1 second and rewind a bit here. Your assignments last week were graded, and grades were posted on Tuesday. So if you haven't logged into Canvas, log in and check out your grade for lab 4. Okay. Also, I hope you saw my email that I sent yesterday that I wanted you to read the text portion of the lab manual, pages 33 through 39, so you would have some sort of idea what we're doing today. If we talked about this back in week 1, if you haven't done so already, please go back and read pages 1 through 4 at the very beginning of the lab manual that goes over stuff we covered briefly in our introduction on week 1, but it gives a little bit more detail, and it talks about the laboratory, the yellow books also, which in your case this semester would be the blank lab note sheets. Okay, so go back and read those, and also make sure that before the Zoom meeting each week that you are reading the objective and the background and the procedure for the exercise we're doing in the lab manual before you get to the Zoom meeting. So this is not all brand new material. You'll at least read it a little bit and have some sort of idea what we're going to be talking about in the Zoom meeting. Okay, so that will be something you should be doing every week. Okay. All right. So we're doing a leveling exercise today that's different than what you've been doing the last 2 weeks in lab. It's not a differential level where you backside a known elevation and you go in a loop around a figure, and you end up with your last foresight back on the manhole. Today we're doing something that's completely different, but it's just a different way, a different type of leveling. I guess you define this more as like a topographic leveling exercise, where we're backsighting a known elevation like we have to do in any leveling exercise, because you need a known point to start with, and we're calculating the height of an instrument, but all subsequent measurements after that are all foresights. Okay, so keep that in mind today. You won't be going in a loop. You're just going to be going basically in a straight line across the bridge. So there are no correction calcs to make because we haven't closed back on our original known elevation. So you're just calculating a series of elevations based on several foresights that you're going to be measuring as you go across the bridge, okay? So on the screen, you'll see similar photos. It's showing a picture of the Guy West Bridge in figure 1. And then it's pointing again to TBMW at the manhole that you're going to backsight in figure 2. Okay, there's the picture of the manhole again. And here is showing the point, the location on the bridge where we're going to be setting up the instrument. Because the bridge has curvature to it and its highest point is in the middle, we have to be careful here, because if we put the instrument too low on the bridge, when the signal is emitted from the laser, it won't be able to go across the crown of the bridge in the middle if the instrument's too low. So we have to set it up high enough on the bridge where the level can go over the crown in the middle and all the way to the other end of the bridge. But if we go too far up the bridge, then we might not have enough height on the rod to backsight on the manhole. So it's a tricky decision there where to set the level up. But where the arrow's drawn here is typically where we would set it up. If there's any questions, let me know as we go along. I'm going to draw all of this on the whiteboard in a plan view, looking straight down a little later on in the meeting today. Okay, so there's only 3 pages here of descriptions. We're going to refer a lot to the lab manual today. Okay. Here's just a picture of the end of the bridge where you would be taking your first measurement, right where the railing starts. Okay. Using the same equipment, you're going to have a tripod with the laser level mounted on it and a leveling rod to take the measurements. And I'll go over how you're going to read the signal from the laser level here in a minute. Okay. Here are the foresights and the one backsight that you're going to use to prepare your assignment. Okay, this is what you would pretend that you went out and measured today with the instrument. Okay, so you have one backsight and everything else is a foresight. You can see the first measurement is bike path west. That's right up here at the very beginning of the bridge where the railing starts. You take a measurement on the concrete at the beginning of the bridge. Mid-span is the next measurement. That's halfway between the beginning and the tower. And then third measurement is at West Tower, which is the western tower of the bridge. And then go all the way across to the other side till you get to the East Tower. And then you'll have another mid-span on that end. And then you'll have the end of the bridge called Bike Path East. Okay. And I'll show you on the whiteboard where all of these are located. You're going to take a measurement to the lamp posts that are on the bridge. That's where your foresights will be taken. And when you log into Sac State website, there's a picture of the Guy West Bridge, and you can clearly see the lights there, and you can see them here too. But when you log in to the website, there's a good picture there of the bridge that you can take a look at as well. Okay, so that's all we have here in CE9L exercise 6. I'm sure there's a lot of questions, but feel free to ask. Now I'm going to go into a little bit about the laser level, and I'm going to switch files here. Okay. So I'm going to bring up some pages right out of the lab manual. You can refer to the lab manual if you have it in front of you, or you can just look at it on the screen here. Okay, here we go. This is in the Files tab in Canvas, Exercise 6 Lab Manual Pages.pdf. Okay, so first of all, the laser level. Here's a picture of the laser level. This is a really old photo, by the way. This was taken probably at least 10 years ago. Regardless, that's an old model laser level. The laser level is an instrument that has a little cap on top of it that has a lens in the side of it. It's a little cylindrical shaped cap, and the lens emits a laser beam from it. It's a red, infrared, but it's not infrared. It's a visible red line, and then the laser will rotate once you turn it on. So when it spins, it creates a horizontal plane of light. So this laser takes the place of somebody looking through the instrument and taking a measurement on the rod. Okay, this thing will level itself once you get it to within a certain range. Turn it on, you can hear the gears inside leveling it, and once it's level, it will start rotating. So the level plane of light would be comparable to you looking through the automatic level and just turning it 360 degrees, and you'd be getting a vision, if you're looking at the horizontal crosshair, of a horizontal plane. The reason that this instrument is popular, especially with construction, is because it eliminates the labor cost of an instrument person. There's nobody standing there taking readings through a level. So it's not only eliminating the labor cost of the instrument person, it's giving you a measurement much faster also, okay? And when we go out in the field, typically with our 4 crews, all 4 crews will work with the same instrument. You're not going out, each crew's not bringing out a laser level with them. There's just one laser level. So you can have as many people as you want taking measurements from this laser level, just depending on how many receivers that you have. So each crew would have a receiver that would read the location of the laser beam that's emitted from it, and you have unlimited number of people who can be working with one laser. This instrument is really accurate for construction purposes. It's accurate to maybe 1/100th of a foot, but because it's based on a beam of light, the farther you get away from it, the less accurate it becomes, because the beam starts dispersing. It just spreads bigger as it gets farther away from the instrument. So this instrument that we currently have is only a year or two old, and it can reach all the way across the bridge with a pretty good degree of accuracy, still probably within a 1/10 or excuse me, 1/100th or 2/100ths of a foot. Normally that's not accurate enough for surveying purposes, but it's certainly accurate enough for construction. Okay. I'm going to go down and show you a picture here of what the receiver looks like. Right here in photo 1 is a picture of the receiver. Up on top, there's a little window. You really can't see it really closely here, but there's a little vertical window in the top left corner there, and you can see a white line passing through the middle of it. That's where, and you notice if you project that white line across to the top of the bracket, that is where you would take your reading on the rod. So this instrument has arrows, and I'll draw these arrows on the whiteboard later. And you can visually see if the receiver is too high to read where the level point of the laser is pointing. And there's also arrows on the bottom that would point up. So there's arrows on the top tell you need to lower the instrument or lower the receiver on the rod, or to raise the receiver on the rod. And there's also audio. The instrument or the receiver will beep. And if you're too high, it's a faster beep. It goes like beep, 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 beep. And then as you get down toward the point where it's level and reading the beam exactly where it should be, you'll get a solid tone. That's where you're level. That's where you would lock the bracket on the rod and take your reading at the top of the bracket. For instance, here we're looking at probably, because this rod is 7 feet tall, you can see the 7, half of it's hidden. But this bracket is set right now at 7.000. That's the reading at the top of the bracket. This arrow designated A is pointing at the middle. That's incorrect. You do not take a reading at the middle of the bracket. You take the reading at the top of the bracket, because that's where the laser beam is hitting the receiver, where the plane is horizontal. Okay. So you can take readings real quickly with this receiver, because you're not taking the time to focus an instrument, to try to sight the rod, to find the rod. And if you had gone out with the level in the field the last 2 weeks, you would know that most of your time performing that lab outside is to get the instrument set up, get the instrument level, finding the rod, focusing the level, and then finally taking a reading. It's probably 10 to 50 times faster using a receiver like this, because you're not trying to find a rod and you're not trying to focus it, and you're not really taking a reading through an magnified optical device. Okay. Questions so far on how this laser works? It's hard to describe it verbally. You really have to see this to understand it. But we don't have that luxury here this semester. So I'm trying my best to try to verbally explain how this instrument works. Are there questions so far on how the laser works? It emits a plane of level light, and you use the receiver to find that plane of level light, which equates to looking through an optical instrument and achieving the same result. So questions on how this works? The receiver is mounted to this bracket, and you slide the bracket up and down, depending if you're too high or too low, depending on the sound or the arrows. And then when you get a solid tone, audio-wise, a solid beep, or you see a solid bar in the little window, that's where you are at. That's where you have now reached the horizontal plane being emitted by the instrument. Okay. So questions on how this instrument works and how the receiver works? Okay. So let's go back up here. Let's talk a little bit now about how you would take your back sight. if you noticed on the previous document, CE9L exercise 6.pdf, when there was the data that I showed you with one back site and the series of 4 sites, the back site was over 11 feet. And you're thinking, well, how in the world are we going to get this receiver up to 11 feet? You know, we can't reach that tall. So how do we possibly take this measurement? If you remember, we didn't talk about it much in lab 3 or 4, but the ribbon there's 2 ribbons on the face of the leveling rod. One of them is 0 at the bottom, and it increases as you go up. If you turn it around and you extend it, you will see that you have a 7 at the top of the rod, and the ribbon, the numbers get higher as you go down the rod, which is backwards of what you would do normally. But here's how you would take a reading to get your backside if it's up in the air, as the backside here is going to be. So look at step 2. You can see how high up in the air that receiver is in order to get the backside, in order to see the signal that's being emitted from the instrument up on the bridge. Okay, so you would you'd mount the bracket at 7.00 at the top of the rod, and instead of physically moving the receiver on the rod like you would do in a normal reading that is less than 7 feet, with this one, the bracket and the receiver stay in a fixed position at 7.00, and you raise or lower the rod until you get the solid beep. And when you get the solid beep with this instrument up in the air like it is, that's where you will take your reading. And you don't take it at the 700. You go down from the top of the ribbon on the back side of it, and you can see that as you get lower on the ribbon, you see here they're down at 9.1 whatever. You see the person with the pencil is pointing to the top of a little brass bracket that's attached to the rod, and you take your reading at the top of that brass bracket. That tells you that the receiver that's mounted up at 7, you're actually at elevation 9.115 roughly here, if you look at the top of that bracket. Okay, so that's how you take your backside measurement. The receiver is at a fixed point on the rod, and you move the rod up and down until you reach the middle of the beam, and that's where you take your backside reading. Okay, again, this is hard to understand. Looking at pictures, it would make a lot more sense if we were physically outside doing this. Okay, but all we can do here is show you photos. Okay, and the book you can see here gives you step-by-step descriptions. If you're taking a reading above 7 feet, here's a little text covering what I just explained. Okay, so if you get a little confused on how this works, just go ahead and read the procedure in the lab manual itself, and it will explain it again. Okay, so that's how you take your backside, and you will need to use this same procedure on your first 2 foresight measurements on the bridge, because remember, the bridge is crown. There's a crown in the middle, and you notice that when you go back and look at the back sights, the sample back sights that you're reading, you're starting at 0.00, at the beginning at station 0 plus 0, 0, and your back sight is over 9 feet. When you get up close to the top of the bridge, that's your back sight, your first foresight will be over 9 feet. That number will decrease obviously as you go up the bridge because you're going uphill. When you get up to the crown of the bridge, you're going to be below measurements of 1 feet. So that's how much the bridge increases in elevation from the beginning up to the middle. It's between an 8 and a 9 foot increase in elevation. Okay, and then once you cross over the crown of the bridge, now you're starting to go downhill toward the other side, and your foresights will then start increasing from somewhere down to lower than 1 back up to over 9 feet at the other end of the bridge. Okay. Come on. There we go. Okay. So there's one error here in step 1. It's to set up and level the laser level at the first tower. This picture is not at the first tower. If you look just above the railing where the cables that support the bridge deck are, this is at the top of the bridge at its lowest point, because that's where the cables are down at their lowest point. As you approach the tower, obviously the cables start getting closer to the tower and they will eventually go over the top of the tower. So this picture is not at the tower. This is at the top of the bridge. So that's a little erroneous there. And here's, if you could look down in step 4 here, you can see where the cables at their lowest spot up at the center of the bridge, and they increase in height. Okay. And you can see the lamps a little bit closer here too. Here's where you will take your readings as you cross the bridge at the location of these lights on the right side of the bridge. Okay. Here's a little closer picture of the laser itself. Oh man, I'm having trouble zooming here. Yeah, it's going to get blurry as we go a little closer. So, okay. That's really all I need to show you here on this particular page. And we've talked about that. Okay. Let's go over to the data that you're going to be entering in on your lab book / blank lab note sheet. Okay. Over on the first column is point, TBMW. They call it TBMB this week. That's fine. We'll call it TBMB this week. That's the same location that you took your back sight to last week. And that's the same location, the manhole, that you established the elevation on in lab 3. Okay. So go back, grab your elevation from last week of the manhole that you used to start your level loop in lab 4. Okay. Bike path west is the beginning of the bridge. Midspan is halfway between the beginning and the tower. And then there's the lights. You'll see here down at light 5, it says turning point 1. This sample assumes 2 instrument setups. When this lab was first created, I don't think the lasers had enough distance to be able to go all the way across the bridge and be visible. Well, the newer lasers that we have can do that now. So we only have one setup that you see there. That's our original setup at the near the east or the west tower. Okay, and that instrument will be able to project that plane of light all the way across the bridge to the eastern side. There's no reason to have to move the instrument to the other side of the bridge to take measurements on the east half. We can do it all from one setup now. So disregard that turning point one and that second back sight and that second height of instrument. You won't have that. You will only have one. So just disregard TP1 there at lamp 5 and the back sight there in the foresight. That will not be there. Okay. So once you've taken these measurements, the last part of your assignment this week is you're going to draw a profile of the bridge to scale. So you will need your engineer scale this week. I talked about that briefly in the introduction in week 1. Okay, you'll need a scale, and this bridge will be drawn to 1 inch equals 100 feet horizontally, and we'll get to that in a minute. But in order for you to plot a profile, you have to have some distances on your horizontal axis. So we're not going to send you out with a tape measure to do a taping exercise all the way across this bridge. We're going to give you some distances that you're going to assume, and those are over there in the delta distance and the station columns. Those will be the distances that you're assuming between each point where you are taking a foresight. Okay. Also, you're going to show the station, which is the cumulative summation of the distances as you cross over the bridge. Okay. You will this week, I've always told you up to this point, all the numbers in here are fake, they're pretend. This week, the distance information and the stations are correct. You're going to actually copy those distances onto your blank lab note sheet, okay? But the backside, the HI, and the foresight numbers are all made up. We've given you numbers to use to calculate the elevation based on the backside and the foresight you're giving. You're going to calculate the height of instrument, and you're going to calculate all the elevations based on the height of instrument and the foresights all the way across the bridge. You can see here that at the end of the bridge on the west side, you've got a foresight of 8.22, and the numbers decrease. These numbers are really fictitious. That number is over 9 feet when you go out there in reality, and it shows you the bike path on the other side is like 3.5 feet taller. That's not correct either. The bike path west and the bike path east foresight will be fairly close because the bridge, the elevation of the bridge in reality is really close to the same on each end of the bridge. It's not 3 feet higher on one end. So these pretend numbers in the foresight column are made up. So don't, just note that your numbers will decrease until you get to the center of the bridge, and then they'll increase as you cross the crown of the bridge going to the other side. Okay. The horizontal distances shown in the bottom left corner of this sheet, you do not need to put that in your book. That's there for your information because you're already showing in the delta distance column the correct distances based on the data that's down in the bottom left corner. Okay, so you just be repeating something that you're already showing in the data chart. All right. This week, you're not going to have an extra row between your turning points and your benchmarks to put the height of instrument on, because you've only got one height of instrument today. Everything else is a foresight. All right. So you don't need to put extra rows in your assignment this week. Okay. So in your yellow lab book / blank lab note sheet, you will create the chart on the left with the back sight we gave you. You'll calculate the height of instrument, and you'll use the foresights given to you in CE9L exercise 6.pdf that I showed earlier in the Zoom meeting. You'll calculate the elevations, and you'll just copy the distances and the stations from figure 6-1 here, because those will be the same. Those are not going to change. Okay. And then on the right, everybody knows what to do over there. The equipment today, you're going to put laser level, LASER LEVEL. Okay. And I think we're getting to a point where you're not going to have an option of putting smoke in the conditions row, which is good. Down where the picture of the manhole is, again, you're going to put TBMB elevation. It's not 50. It's what you used last week. Most of you ended up using 45.466 or something close to it. Okay. So that's the number that you're going to start with at the manhole today, just like you did last week. Okay. Any questions on anything so far? Okay. Nobody has any questions at all?
So far, so good.
Okay, good. I just want, sounded like everybody, it sounded like I got muted or something here and nobody was hearing anything. Okay, so sounds like everybody heard everything. Okay. Students really like this lab. It's fun because you realize that it's so much quicker using an instrument like this than setting up a level and trying to take a reading through a magnified scope. It's very fast because the instrument basically sets itself up. You put it on a tripod, you eyeball it to get it somewhat level, turn it on, it levels itself, and boom, you've got an instant plane of horizontal light. Okay. So it goes really quickly once you figure out how to move the receiver up and down, move the bracket with the receiver attached to it up and down the rod. Okay. So in your for your assignment this week, you will submit figure 6-1 with the sketch on the right and the data table on the left. Okay. And let's talk a bit now about what your profile drawing is going to look like. Okay. You need to use graph paper to draw this. Do not try to draw this on a blank sheet of paper and try to draw rows to the correct distance and try to plot this thing. Again, I can't rotate this image on the screen. You're going to have to turn your whatever device you're using to be able to read this. Correctly in the right position.
Is engineering paper okay? I'm assuming for the drawing.
Oh yeah, okay. Engineering paper. In fact, most engineering paper, if you have the paper that's sort of a light green color with the graph with the graph lines on it, or the grid lines on it. Most of those engineering papers have lines that are at a scale where you can drop a scale on it and directly, read over 5 lines and you're at 100 feet. So yeah, you definitely engineering paper will work here. Okay. Let's zoom this thing out a bit. Oh man, come on.
I think in the top right where it says Zoom.
Now
If you
there we
click there.
go. Okay, yeah, but I don't have an option to go. Well, we'll have to do with what we have here. Okay. First, I want to discuss the scale here. This is, we talk about, we don't use inches in this class. Well, we don't use inches to measure anything. We use decimal feet. Everybody understands that now after 4 weeks. But when you're preparing a drawing, even though you're measuring to decimal feet between the whole feet, when you print something or prepare a drawing, you're still using English units, okay, of inches. That's how you measure measure distances on a plan sheet, okay? So even though we don't measure with inches in surveying or engineering, we draw in inches, okay? So when you draw this, make sure you draw the horizontal scale at 1 inch equals 100 feet. Does anybody not know how to use an engineering scale? You've got 6 scales on there, 10, 20, 30, then you turn it around. And on the other end, you've got 40, 50, and 60. Those are just ratios. If you're drawing 1 inch equals 10 feet, you're still using the 1 and 10, you're using the 10 scale. If you're drawing 1 inch equals 100 feet, you're still using the 10 scale. It's just that if it's 1 inch equals 100, your graduations at the lines on the scale are 10 feet. If you're drawing 1 inch equals 10 feet, the lines are only 1 feet, okay? So know the difference there. I had a couple students that were confused last semester. Hey, I only had a 10 scale. I didn't have a 100 scale. Well, they're both the same, okay? It's just the ratio is different. In engineering drawings, what we're trying to emulate here, you're going to be drawing at a vertical scale of 1 inch equals 10 feet. In engineering drawings, the vertical scale is always exaggerated by a factor of 10. Because if you are drawing, and I'll give you an example when we get to the whiteboard, okay, you're trying to exaggerate that vertical scale just for clarity purposes. If you are, for instance, designing a road and you have all of the underground utilities shown in a profile view, if you do not exaggerate the vertical scale, all you're going to see are a bunch of lines that are running all on top of each other. By exaggerating the vertical scale by a factor of 10, you're stretching out that room for the vertical improvements that you're trying to show. You've got, a water line, a sewer line, storm drain lines, electric utilities. There's all kinds of underground things that you show in a underground profile on an engineering drawing. So it enhances the clarity when you exaggerate it. And I'll try to show that on the whiteboard as well as an example. Okay. So you can see that by drawing it exaggerated vertically like this, the crown of this bridge looks huge. Obviously, when you're walking across that thing, it's not that steep. But for engineering purposes, it will be. And it's even true for roads. We exaggerate scale when you're drawing a road by a scale of 1 to 10 too. So again, just realize what you're looking at is exaggerated, but it's exaggerated for a reason. Okay. So just here to show you, if you go from station, your horizontal scale will be in units of stations. You're going to label station 1 plus 0, 0, 2 plus 0, 0, all the way across to 8 or 9, depending on, well, your distances aren't going to change here. You're only going to be going to 8 plus, you know, whatever it is, okay? Vertical scale, make sure you put the first row, the first labeling vertically, it's got to be less than, you probably want to start at 40 there, because your most likely your manhole is going to be around 45.466, and the bridge is going to be a little higher than that. So make sure that the number that you start labeling your vertical scale at is not lower than 45. Okay, so when you get up to 50, you'll be a little bit above the bottom of the drawing. So if you're to look at the distance between the beginning at station 0, 0 and over where station 1 is, and then look vertically where 50 is located and where 60 is located, that's 10 feet vertically, but it's the same distance on the piece of paper, 10 feet vertically, as the 100 feet horizontally. Okay. So there's showing your exaggeration, vertical exaggeration of a factor of 10. So make sure you draw this at 1 inch equals 100. When you draw this, at the top where it says Guy West Bridge Profile and it says not to scale, it's saying that the drawing in the lab manual is not to scale. You're going to draw this thing to scale on your graph paper. Okay. Don't use a blank lab note sheet, blank piece of paper. Use an 8.5 by 11 sheet of graph paper, okay? And put your name on it. That will be the second document that you submit along with figure 6-1 that you're preparing on the blank lab note sheet, okay? Okay. But label everything on here as it is shown. You're going to label the stations 1 through 8. You're going to label the vertical lines every 2 feet. You're going to label the lights L1, L2, L3. So you're going to label the west tower. So just plot this thing and draw a dot, you know, at station 1, whatever, station 50, whatever, and just draw the location of the point. Then you'll draw the profile of the bridge connecting all of the points, okay? And then label all the distances between the measurements, label the midspan, label the towers, label it just like it's shown here, and make sure you show a scale, okay? Put scale H is 1 inch per 1 inch equals 100 feet. V is 1 inch equals 10 feet. You don't have to put 8.5 by 11 paper. I'll know that it's 8.5 by 11 paper when I see it. Okay. So I know it's going to be hard to grade this. Normally I would get a scale out and make sure you drew it to scale, but because you were submitting this electronically, I am not going to take the time to print all of these out and measure them. But I can tell by looking at it if the scale is off, at least the the ratio of the horizontal scale versus the vertical scale. That'll be easy to tell if you didn't draw those correctly, okay? So label it like everything, put everything on your sketch that is shown here, except the words "not to scale" that are underneath the Guy West Bridge profile text, okay? This will be drawn to scale, all right? So any questions on what you're submitting this week?
Yeah, so when we're drawing that, would you like us to actually draw those vertical and horizontal lines showing the grid? Or is that just to be
If
assumed
you're
on the
using
graph?
graph paper, you won't need to. If you just
Okay.
label everything with tick marks, if you just put a tick mark above the stations showing where station one, which line on the graph paper is station 1+00, which line on the graph paper is 2. You don't have to draw the entire vertical line. Just put a tick mark at the bottom so I can see which line on the graph paper you're labeling, okay? Same thing horizontally or vertically. Put a little tick mark or a short little line right on top of the graph paper line so I can see which line you're referring to when you put the elevation in increments of 2 feet, okay? So no, you don't need to enhance the grid lines like it's shown here. You just draw it and then just make sure you clearly label which of the graph paper lines are the elevation that you're labeling and which graph paper line is the station that you are labeling, okay?
Thank you.
Okay. So I'm going to go on over to the whiteboard now and kind of show you a little bit more here. I'm going to draw, you know, where these points are that you'd be measuring to, looking down in the profile view, okay? And try to draw a little better picture of that receiver and what you'd be looking at if you were taking measurements on it, okay? So if you have any questions as we go along here, I don't think there's anything else on here I want to show you, okay? Okay. By the way, this week, I started deducting points if I see overwriting and erasing, just a heads up. So I will deduct points if I see that from here on out, okay? And I think only a couple students in both Thursday sections got points taken off for overwriting, okay? So make sure you don't do that. Okay, I'm going to switch over to the whiteboard. And let me grab my iPen. Okay. Let's see here.
Professor?
Yes.
I just noticed in the example, for the actual part where we write down all of our calculations and things, there's an extra column compared to the papers that we have. Do you want us just to split one of those columns?
Yes. Yes, I forgot about that. You'll notice that the sample in the book has 1, 2, 3, 4, 5, 6, 7 columns. Okay, your paper, your blank paper only has 6. So let me erase this and show you what you need to do. Okay. So you've got 2 sides to your paper here. And you've got your 6 columns over here. Okay. I'm not going to take the time to draw all these things, but 1, 2, 3, 4, 5, 6. So over here will be your delta distance. And here's elevation, foresight, HI, backsight, and point. So on the right side of the paper where you normally put your name here, okay, just go ahead and draw another column. And label it station. Okay, that will be on the right side of the page, which will mean you have less room to draw your sketch information, but you can fit it all still on the right side over here. You'll just have a little bit less room across the page because you're adding this station column on the right side of your book. Okay, make sure you line up the distances vertically. When people try to do this in the yellow book, sometimes they forget, and then they turn a page and they put the station column on the very left-hand side of the next page. So you're having to turn backwards, and when this gets drawn, it doesn't align correctly with the same lines over here. You won't have that problem on this blank sheet of paper. So just make sure when you continue this column, in other words, don't draw it with, say, station up here, and then you've got your first row of data higher than here, and this doesn't align. You've got it doing the zigzag here. Make sure when you draw this, you've got station here, and your data will all align. The station here corresponds to all the data on the left side of the sheet. Okay. So any questions on that? Thank you for bringing that up. That's definitely something that needed to be discussed. Okay.
And so
Okay.
we just
I
use
have a question.
that empty.
Yeah.
On the subject, I've noticed that in my previous labs, you've said I need to use format with extra row. I'm kind of wondering what you mean to fix it.
That only applied to lab 3 and 4.
Will it apply for future labs?
No, because we're not doing any more differential leveling exercises this semester. It's only for the differential leveling exercises, which are lab 3 and 4, where you've got a series of backsights, foresights, height of instrument, backsight, foresight, height of instrument. This week it doesn't apply because you only got one backsight and one height of instrument, and everything else is a foresight. So no, you don't need to use the extra row here. The extra row is just to clarify for you which backsight and which foresight is connected to which instrument height. Okay, that was the whole reason for doing that. Okay, so
okay,
you don't
thanks.
you don't need to do that this week.
Got
Okay,
it. Just wanted to confirm so that way I don't make future. That's all.
Okay, no, that we're done with, in fact, this will be our last leveling exercise. Next week, we're going to start doing angles and distances. Okay, so this is the last week you'll see any back sights and foresights also. Okay, let me draw the bridge here. Yep. Well, I'm not going to redraw that. It's just a sidewalk. All right, and you have the manholes here, our fourth manhole. Here's our temporary benchmark, which is called TBMB this week. All right. And here is the beginning. Here's the end. So here is station 0 plus 0, 0, right at the very edge of the bridge. Okay. Here's the east tower. Excuse me, west tower. Here's the east tower. Okay. So here is bike path west, as it's described in the lab manual. Here is midspan. Now to station 0 plus 50. And here's the tower, which is at station, here's west tower. Station 1 plus 0, 0. Okay. And then we've got our lights. We've got lamp 1, lamp 2, lamp 3. I'm not going to draw all of these lights all the way across. Okay. You're given a distance here of 50 feet, 50 feet. And then you've got a distance here, 23.9 feet. The reason for that is if you look at the tower, the lights on the other side of the tower, they're staggered. They do something like this. But we're not using the lights on the north side. We're using the lights on the south side. But when the bridge was built, that's why this tower, this first light is so close to the tower. All subsequent lights, the lab manual says 49.9. In real life, nobody would design lights 49.9 feet apart. They'd be 50 feet. All right. Somebody wanted to make more math for you, but all the distances and stations are given to you. Those aren't going to change. Okay. So then you'd have station 1 plus 23.9 right here. And then 49.9 feet later, you'd have station 1 plus 73.8. Remember, stations are cumulative as you go all the way across, okay? And each light is 49.9 feet apart. Then you've got the tower down here. For some reason, this last distance is 50.2 instead of 49.9 that the rest of them are, okay? And then this distance 50 and this distance is 50, okay? So the instrument will be somewhere around here, okay? So you will take a back sight to the manhole, okay? Every other subsequent measurement after this is a foresight, okay? Right here is a foresight. 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 All the way across, okay? Okay, questions on that? Okay, Let me give you just a brief example of this vertical exaggeration. Say we've got a road and we're going to have original ground will be shown as a dashed line. We're looking profile, we're looking sideways now. And then the new road will be looking something like this, okay? And then you'd have curves here. A vertical curve here, a vertical curve here. You'll learn a little bit about curves later on in CE9 this semester, okay? Then if you didn't exaggerate vertically, you would see, you know, a sewer line, and you'd see a water line, and that all these things would storm drain line might look something a little closer to the ground, but all these lines start running together, okay? If you separate them vertically, you would see maybe a sewer line way down here, and you could actually draw the top and the bottom of the pipe, okay? You'd see a water line a little closer to the ground. And maybe a storm drain line as well. And you'd see clear separation of the pipe when you have a vertical exaggeration. If you didn't have it, everything would be scrunched up and you wouldn't know what line you were looking at is for what, okay? So that's why things are exaggerated vertically, is for this reason, just for clarity, clarifying what's actually going on underneath the ground, and it helps you more easily see conflicts where pipes cross, and you have to make sure that they're not touching each other, okay? So that's why things are exaggerated vertically, okay? One last thing, I just want to draw a picture of this receiver. Okay, you've got a series of buttons down here, an on-off button, a volume button for the beep. There's a couple others for other minor functions. But then you've got this window up in the top, and in that, and then you'll see a line going through the center of the window. It goes all the way across, and then the bracket is attached to it. And the bracket is what is attached to the rod, and you take your elevation at the top of the bracket as you're looking at the rod, okay, with your lines going across like that. Okay, you just pretend that this top of the bracket is your horizontal crosshair. Okay, that's where you take the reading on the rod. Okay, over in the window, as you move this receiver slowly up and down the rod, you try to get close to where you think the signal is, and eventually you'll start hearing a beep. And if you're too low, you'll see two large arrows, or three large arrows down here. I'm only going to draw two. It's an LCD screen, so these are dark gray against a light gray background, okay? And you'll hear a quick beep, 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 beep. And as you raise the receiver up, these arrows disappear as you get closer to being level. And eventually, when you get to level, the arrow goes away and you'll see a solid bar going across the window, and you'll hear a constant tone, just beep. Okay, that means that you're level. That's where you take your reading, is at the top of that bar when you see it here in the window, which corresponds to this line that is projected across. Same thing if you're too high, you'll see arrows pointing down, and you'll hear a slower beep, 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 beep. So you can tell by the beep if you're too high or too low, or you can tell by the arrows. There's also a window on the back side of this, so you can stand behind it and point the receiver at the laser, and you'll be able to see that same window on the front of the unit. And if you turn it around, there's a window on the back, so you can stand behind it and see the arrow. So this works the same way. As you lower the instrument or the receiver, the arrows will disappear, and eventually you'll see the black bar show up with the constant tone. Okay. So any questions on that? Or any questions at all?
Professor, I have a question. To calculate the elevations, we usually do the HI minus the foresight, but we're not going to have the HI this time. So I was curious how we're getting the elevation.
What? You won't have an HI this time?
Yeah, because we're not getting backsights, and to calculate the are we going to have HIs, I guess?
Yeah, you have to have an HI to calculate any elevations, anytime, any kind of level. You're going to backsight.
Yeah, but we're only given one.
You only have one backsight, which is the backsight to the manhole. That will allow you to calculate the height of instrument. Everything else is a foresight. You will subtract the measurement on the rod you're reading at all the subsequent points, starting at station 00 at Bike Path West. That's your first foresight. That is subtracted from the height of instrument to get your elevation. So all of your foresights, of course, are subtracted from the instrument height. Okay.
Okay. Yeah.
So,
thank you.
Yeah, the sequence is completely different this week. We don't have backsight, instrument, foresight, move the instrument, backsight, foresight, move the instrument. We have one instrument set up. Well, you can take as many foresights as you want from one instrument setup. Okay.
So are we using that same backsight for all of the foresights?
Yeah, you only need a backsight you need a backsight on a known elevation in order to calculate an accurate height of instrument. Once you've got your height of instrument determined, you don't need your backsight any longer. Okay, so you use the height of instrument in order to deduct all the foresights to calculate all of your elevations. All of your elevations this week, or all of your foresights this week, all of your measurements will be a foresight except the very first one, which is the backsight, which will allow you to establish the elevation of the instrument. And then that will allow you to calculate the elevations on the bridge by subtracting all of your subsequent foresights. So the only difference this week is that you're just using one setup to determine all of these foresight elevations. So just make sure you add the backsight number to the benchmark elevation to get your height of instrument. And then everything you're taking on the bridge is a foresight. Is that clear?
Yeah, thank you.
Okay. That's all I have, I believe. So if you have a question, I, again, will stay logged on until everybody has logged off. So if you have a question, just speak on up. Otherwise, you're free to log off, and we'll talk next Thursday. Again, this assignment's due Monday, regular time, which I think is 1 p.m. I can't find the schedule here off the top of my head, but obviously it's showing in the assignment page, the due date. The due date was Monday for sure. I think it's 1 p.m. Maybe it's 2 p.m. I'm not sure, but turn it in at your normal time on Monday. Okay. So if there's no questions, I'll talk to you next week.